Can you hear me? Fine. My name is Velerio Nascimbeni from University of Padua, Italy, and these are my collaborators, also from Italy. And I will talk about our new observational study of the atmosphere of GJ 3470, which is a hot Neptune, hot Uranus, I would say, made with the Large Binocular Telescope. So these are some basics. We already learned from the previous talks that studying exoplanetary atmospheres is very important. In first place, because by knowing only the mass and the radius of a planet, it is very difficult to tell what is the inner structure of that planet. So because there is a very strong degeneration between different models. And also, it is very crucial to investigate the evolutionary history of the planet. Well, the most powerful way to investigate the planetary atmosphere is transit photometry, transit spectrophotometry, or occultation photometry. And there are two very, complementary ways to study the planet, because in the occultation photometry we see the light of the planet itself, while in the transit spectroscopy we see the light of the star, which travel through the planetary limb, of the limb of the planetary atmosphere. So we can probe for different signatures, for example, from atomic species like sodium or potassium, for example, from molecular band, especially in the infrared, like water, CO, methane, and so on. But we also can study processes affecting the continuum of the planetary spectrum. For example, due to scattering. This is a real photo of Titan, which have scattering from condensates in the higher layer of the atmosphere. This is some example of Rayleigh scattering in action, taken from theoretical models by Howe and Burrows 2012. The simplest case of scattering is Rayleigh scattering, which is very familiar because it has a typical signature which is proportional to the wavelength to the -4. This is the same reason why the Earth sky is blue. And it can be due to molecular hydrogen, like in this set of models of, with a solar scale composition, and you can see the increase of the apparent radius of the planet toward the blue region of the optical spectrum. But it can also due to condensate particles, such as tholins or other compounds. And this is an example of different models with tholin particles with different dimension. And this is the case of Rayleigh scattering. Why it is so important? It is important because it can exploit the measure of the Rayleigh scattering can be exploited to obtain an independent estimate of the atmospheric scale height of the planet. So in this under simplified assumption, if we know if we can estimate the equilibrium temperature of the planet, we can know, for example, the mean molecular weight of the atmosphere. So we can access, we can have a hint about the composition of the atmosphere. This is maybe the most impressive result, observational result to date. This is the detection of Rayleigh scattering from high altitude haze by Singh et al. 2011 in the hot Jupiter HD 189733, made from space-based observation from HST. And you can see that there is a really significant increase of the effective radius of the planets in the ultraviolet and blue region of the optical spectrum. So we want to try to study the Rayleigh scattering in planetary atmosphere from the ground, we choose to use the large binocular camera at the LBT telescope. LBT is a double 8.4 meter telescope in Arizona, and the LBC camera is in fact two different prime focus imager, one at each mirror of the telescope, and this one is is optimized for the blue wavelengths in the optical region, and the other one for the red. And well, first, the first advantage is that the blue camera is very efficient in the U band, and this is very important because if you want to study red dwarfs with these techniques, we need to go really deeper because these are very red objects, and the U flux is very small. And the other advantage is that we can perform simultaneous dual band photometry. We can have at the same time a red and blue light curve. We can monitor telluric and instrumental systematics, which can be very limiting from ground-based photometry. And also we can monitor and try to correct effect from the chromospheric activity of the star, which also can be very strong for M dwarfs in general. So why GJ 3470b? This is a recently discovered transiting hot Uranus, and this is a mass versus radius diagram. You can see the different families of planets in different colors, and you can see that GJ 3470 is a very inflated planet at the boundary between super-Earth and Neptune's. And also its composition is very uncertain by knowing only the mass and the radius. An advantage is that it is orbiting an M1.5 dwarf. So the transit is relatively deep for a Neptune-sized planet. On the other hand, theoretical models expected to have a large envelope of low mean molecular weight for GJ 3470, maybe made by primordial hydrogen and helium. But there is some degeneration among the models, of course. Our observing strategy is high precision differential photometry. If we can carry out photometry in two different bands, it's like to carry out transit spectroscopy with a very low resolution. It is, of course, differential photometry with a net of reference star, or very stable and iteratively chosen reference stars. And we also applied a very strong defocus because we want to collect a huge number of photons without saturated detectors, and also we want to minimize any intrapixel and pixel-to-pixel inhomogeneity in the detector. We choose the U spatial filter on the blue channel, which is very similar to the U filter in the Sloan system, but with a high efficiency. And we choose a intermediate band filter at nearly 1 micron on the other camera. So to cover the largest wavelength range possible. We want to avoid black boxes. We want to have full control over the reduction. So we employed our photometric pipeline, Starsky, which is described in those papers, and which was originally designed for our TASTE project, a project about TTV monitoring from ground-based facility. And we applied optimal weights with this code, and also we decorrelate for systematic errors due to residual atmospheric effects or to the motion of the stars over the detector. These are the light curves. We are photon noise limited in both channels. Of course, the blue curve in the U band is, has a higher noise because this is a very red object, and the flux is very, we are very starved by photons in this band. And it is, well, it is worth noting that the 1 micron, let's say 1 micron light curve is maybe one of the most accurate light curve ever gathered from the ground, from ground-based facility. So the scatter is only 0.28 millimagnitude in the ambient light curve. Fortunately, we did not detect any 5 minutes, any significant, sorry, any significant bump or signature from chromospheric activity from the star. And, well, it is evident that, well, after accounting for limb darkening and activity effects, these are the residual from the fits, that the U-band transit is deeper. So there is an increase of effective radius at the blue wavelengths. We combine our data points, those 2 points. This is the U measurement, this is the 1 micron measurement, with the other point available in the literature for Cui et al. And from Demory. This point is measured by Spitzer at 4.5 micron. And, well, it is clear that there is a significant increase of flux, at least at 6 sigma. And also there is a significant difference with the Spitzer measurement at 4.5 sigma. And we played with some rescaling the models from Howe and Barrows 2012. And we saw that no high mean molecular weight model, such as a water-dominate or methane-dominate model, is compatible with our measurements. If we choose a low mean molecular weight, such as an atmosphere dominated by helium and hydrogen without clouds and without haze, the situation is better for the red and infrared points, but still we cannot reproduce this very steep increase of radius in the blue region. So there is another source of scattering other than molecular hydrogen. And indeed, if we try to scale a model with a haze, high altitude haze with small particle of tholins, we are able to get a satisfied fit of all our spectral range. So maybe this is an explanation, but of course other observations are needed, maybe at higher resolutions. And at the end, this is a very nice test that we can do. We use our residuals in the red light curves, the most accurate one, and we inject in those residual a transit which is 0.3 millimagnitude deep, which is the transit of 1 Earth radius planet around the star. And you see that theoretically we are still able from the ground to detect a 1 Earth radius transit with a 9 sigma significance. So this maybe could be a possible way in the near future to detect planets which are already known from radial velocity, and we can have an observational window and try to search for the transit of the planet in that window. Okay, thank you.
Thank you, Valerio. Any questions? Oh, down there, yes.
Hi. Did you use similar as comparison stars to Gliese 3470? Do you use something which has a similar color? Because in the blue that would create quite a difference.
Yeah, it is very difficult to find in the field a star which has the same the same color of an M dwarf, and the vast majority of them are giants. So they are excluded by our iterative processing. However, we can, this is a pure differential measurement, and in the process, there's been also a detrending of the out-of-transit part of the light curve. So if there are problems with the colors of the reference star, we expect that there is an air mass effect. So it is a very smooth and long-term trend. And you can decorrelate by looking at the out-of-transit flux of the light curve. So it is not a big problem.
Yes, up there. Oh.
Hi, I was just wondering how much the uncertainty in the limb darkening parameters you use influence your final error bars.
Well, we fit for the impact parameter of the planet in the red light curve because it is the most accurate one. And then we fix in the Monte Carlo simulation the result for the impact parameter, which is a purely geometrical parameter, when fitting the blue light curve, which is that one with a higher level of noise.
Sure, but you don't know what the limb darkening parameters are, whatever.
Yeah, we can fit the limb darkening parameter in the red channel, and we assume the theoretical values from Claret 2011 for the blue, because essentially you cannot fit on this curve for the limb darkening parameter.
Okay, yes.
Okay, just a quick question, naive one. You mentioned tholins in the atmospheres of these planets to explain the properties that you observed. I remember a few years ago I made an internship of the data that the Huygens probe collected on Titan, and we're trying to model the actual spectrum of the ground of Titan with tholins, and I remember that the optical properties, the optical transmission of the tholins were not well known at this time. How far do we know this kind of things actually?
Well, this is only a very qualitative approach, just to see which class of planet or atmospheric model can be rejected. Okay, but we are still at the beginning to investigate this planet. Well, the only thing we are, I am sure, is that there is an increase of radius at shorter wavelengths. But
Okay, thank you.
2 more questions. Yes, right at the top.
Eric Gaidos, University of Hawaii. This is very nice work, and it's very impressive, so I'm looking forward to the publication and future transits. As I'm sure you're aware, one of the other effects you have to worry about is the unocculted spot effect. Can you comment a little on that?
Yeah, we calculated, there is a paper already submitted on this work, and this aspect is discussed in the paper. We calculated the effect for the correction on the effective radius of the planet for unocculted planetary spots, star spots. And we calculate a maximum correction, and we noticed that even after applying the maximum correction, there is still a very significant increase of radius in the blue, at least at 4 sigma. So activity cannot be the only explanation.
Okay, and the last question up there. Sorry, John.
So this U-band result is very exciting. It's too bad you had to defocus to keep from saturating in the red, because that's probably limiting your U-band precision because the star is so faint there.
Yeah.
Is it possible to introduce a different focus to the blue and red channels?
Yeah, but we already applied a different focus in the U and the red band. The problem is that we at the moment, we need to choose the same exposure time. And this is the limiting factor.
Great, thanks.
Okay, let's thank him once again.
Thank you.